I've got 12 minutes. Let's see how quickly I can explain this. This section of your textbook includes this crazy formula. And the idea is this. If you are given like a long list of coordinate pairs, right, like x comma y, so if you're given the point 1, 2, and you're given the point 3, 5, and you're given the point -1, -4, like I'm just making a list of like things, right? And so you have some long list of coordinate pairs. And so on an xy plane, I don't know what it looks like exactly, but I'm just going to plot a bunch of points that are hanging out on my plane. There is one specific line that belongs to the xy plane called the least squares regression line that minimizes the vertical distance between those orange points and this blue line. Yeah, so what we're trying to minimize is this vertical distance between each point. We'll call it dk for point k. What I'm trying to do is minimize the sum of all of the points distance squared. We're trying to minimize this. And so you can think of this as like trying to find the minimum of a multivariable function. And I mean, it's a clunky way of thinking about it, but it's possible with this being my multivariable function that I'm trying to minimize. So your textbook gives you this formula for finding the formula of the line, right? So that's slope-intercept form of a line. And it says if you want to find the slope, that is what you would have to use. And if you want to find the y-intercept, that's what you would have to use. But if you look at that, how many things do you have to multiply and add together? Like, that's disgusting. That's it's the dumbest way to do it. I'll say that. If you were taking a statistics class, they would teach you how to find this least squares regression line by finding things like the mean and the standard deviations, and you could come up with a slick, easier looking formula than this mess that you see before you right here. But we're not in a statistics class. The easiest way I can think to explain this is with linear algebra. So in linear algebra, we have this kind of solution to things. This is what we would do. If you have 2 points, and the points are 1, 2, 3, 4, right? And you want to find a line that passes through those 2 points, here's what you do. You come up with a matrix, and this matrix in the first column is going to be all 1s. And then in the second column, we're going to put my x variables. So it's going to be 1 and 3 because my x coordinates are 1 and 3. Okay. Then we multiply that matrix times a vector that contains my y-intercept and my slope. And I expect the product of this matrix vector multiplication to be 2, 4, because those are my y-coordinates. So if you think about how do I get this 2 entry using matrix vector multiplication, I would take the dot product of the first row in this vector. So it would be b times 1, which is just b, plus m, my slope, times my x variable. And that should be equal to the corresponding y value. Okay? Then for this entry, I've got b times 1, which is just b plus my slope times my x value, and it should give me the corresponding y value. And so that always works. And that means if you want to find the slope and the intercept, all you have to do is take the inverse of that matrix, or you could solve using Gaussian elimination, times the vector with the y coordinates. Okay? So this also works if I want to interpolate 3 points using a quadratic function. All I have to do now with my matrix is make a 3 by 3 matrix, where again the first column is all 1s. The second column is going to be my x values, so 1, 3, and 5. And then the third column is going to be my x values squared, which is going to be 1, 9, 25. And then I multiply this times the vector CBA, and I expect the result to be my y-coordinates, 2, 4, and 7, okay? Because again, think about how I would get this 2. I would take the dot product of my first row times this vector, so it would be c plus b times x plus a times x squared. Should give me my y. This would be, again, c plus b times x plus a times x squared, and again, that should give me the corresponding y value, and you kind of see what this is doing here, what's going on. All right. So that gives me the interpolating polynomial. That means, like, if I have 3 points, right, that gives me exactly the parabola that passes through all 3 of those points. We haven't yet solved the regression problem, but I wanted to show you the interpolating problem first as kind of an intro to the regression problem. By the way, you can do this with any degree polynomial. If you want to do a cubic polynomial, you would have to supply 4 points on the plane. You could find the cubic polynomial that passes through those 4 points. If you wanted to use a quartic polynomial, you'd have to supply 5 points. And with 5 points, you can find the quartic polynomial that passes through all 5 of those points, just by making that matrix bigger and making your vector bigger and so on. Okay, so now I'm going to say A is the matrix where you have 1s in the first column, you have x's in the second column, you have x squareds in the third column, and so on, right? Then this vector is going to be the vector of coefficients, starting with your constant and then your linear term and then your quadratic term, constant, and so on. And then this is going to be the vector with all of my y values. Okay? So the matrix I'm calling A, this vector I'm going to call C, and this vector I'm going to call y. The solution to the interpolating problem is you take C equals A inverse times y. But if you want to have a bunch of points, but you only want to plot a line, then this matrix is not going to be square. And if you don't have a square matrix, then you can't take the inverse of it. And so what we do instead, to make it a square matrix, is we're going to take this, what do you call it, matrix vector equation. And then we're going to say, multiply both sides of this equation times the transpose of the matrix A. And then A transpose times A is going to be square. And since it's a square matrix, then I can take the inverse of it. And that is the solution to the regression problem. So this vector is going to contain the coefficients of the regression polynomial. Man, I'm going to run out of time because I tried to talk about too much today, but if I have this matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. What I mean whenever I say the transpose is this. Oops. Not the whole matrix. There we go. Do you see what happened? The rows become the columns, and the columns become the rows. So you take the matrix and you mirror it across the diagonal. The diagonal remains the same, so I still have 1, 4, 9 on my diagonal, but then everything else flips and mirrors across the diagonal so that your rows become your columns become your rows.
So instead of when P, because Pn, the dimension.
Yeah. So what if I gave a whole bunch of points that are coordinate pairs? So this is an x coordinate and a y coordinate for all these points. Really quickly, I'm going to try to show you just the linear polynomial regression problem. So the matrix A would be the matrix where I have a 1 in the first column, right? All 1s. And then my second column would just be the x values, right? So this is not a square matrix. This is a matrix with like 9 rows and 2 columns, not square. But the transpose, A transpose, sorry, let me have 3 more minutes here. If I do transpose of this whole array, close parentheses, and then I'm going to have to find exactly the right size so that Excel will do this for me. Oh, I forgot an S. Transpose, not transpose. There we go. So that's A transpose, right? Now, to get the square 2 by 2 matrix, I'm going to type in equals NMULT for matrix multiplication of the A matrix, comma, the A transpose matrix. So I'm multiplying those 2 matrices. I get a 2 by 2 square matrix for multiplying A transpose times A. Now, like I said, I want to find the matrix inverse of this little 2 by 2 square matrix. And I forgot to, okay, there's the matrix inverse of that. Then, what do I need to do next? I need to multiply that inverse matrix times my transpose matrix times the y values. So, almost there. This is going to be the matrix multiplication of my transpose matrix times all of my y values, and it's going to be a resulting 1 by 9. Nope, sorry, it's going to be a resulting 2 by 9, I'm pretty sure. No, it's just going to be a 2 by 1 matrix. Okay, so now the last thing I need to do is, matrix multiplication of that matrix by that little vector. Boom, except this is going to be 2 by 1, so there. So now, in this little vector, we've got the slope and the intercept of the regression line. Now, that seemed like a lot of work, but the cool thing about the sort of linear algebra solution is that the formula is really easy to remember, and this works for any polynomial. It doesn't just give me the least squares regression line, like this formula from the book does, but this also could give you the least squares regression parabola, or the least squares regression cubic function, or the least squares regression quartic function, quintic function, 6th degree polynomial, 7th degree polynomial, etc. And so it's a lot more powerful for that reason. If you want to fit any other kind of math model, you can use that instead.